Hello everybody, this is Dr. Christopher White and welcome back for the second half of the Cenozoic Earth history presentation. So in this one we're going to be looking at the most recent period in geologic time, so we're going to be focusing on the Quaternary. Okay, let's get going. So the Quaternary period extends from about 2.6 million years ago until the present day. So the start of the Quaternary is marked by the beginning of the most recent ice age. Now, the Quaternary consists of two epochs, the Pleistocene, that goes from about 2.6 million years ago to about 12,000 years ago, and the Holocene that goes from about 12,000 years ago until the present day. So the transition between the Pleistocene and the Holocene is marked by the end of the most recent ice age. Now, there has been some discussion recently about whether we have entered a new epoch, and the suggestion has been that this new epoch should be called the Anthropocene. So the argument goes is that human beings have had a substantial effect on the Earth's surface, and as such that effect is going to be visible in the rock record. So if you were to go 5 million years into the future, and if you were to look at the sedimentary rocks that are forming right now, you would see in those sedimentary rocks indicators of human existence. So you might see things like, you might be able to detect certain radioactive isotopes associated with the testing of nuclear weapons. You might be able to see changes in carbon isotope ratios associated with human beings burning fossil fuels. You might also see the onset of a mass extinction event because human beings are causing a very, very rapid decrease in the diversity of flora and fauna on the surface of the Earth. And all of this will be reflected in the rock record. And so they've gone and said, because human beings are having this effect, we've essentially transitioned from the Holocene, where essentially the Earth was functioning as a normal system, to the Anthropocene, where essentially the Earth is having the effects of human existence being superimposed onto it. So we can see those in the rock record. Now, the question is, what boundary do we use to say, right, this is the start of the Anthropocene? Well, there have been three main boundaries suggested. The first one is 250 years ago, and it would be the onset of the Industrial Revolution. Now, this is going to be reasonably easy to, well, this would be, should I say, relatively easy to spot in the rock record, because you would see a change in carbon isotopes associated with the burning of fossil fuels, and you would also see the onset of a mass extinction, because it's only really in the Industrial Revolution where human beings really begin to pick up the rate at which we've been causing certain flora and fauna to become extinct. Now, the other two options are 2,000 years ago, so that's called Antiquity, and at this point we have the arrival, or the rising up, should I say, of several major civilizations. And so we'll begin to see in the rock record, we would see indications of the surface of the Earth being adapted to those civilizations. So for instance, we would see things like wide-scale deforestation associated with the need for fuel for these very large groups of people. Now, the final option is that we would set the boundary to about 8,000 years ago, which is the first appearance of farming. And so in this case, we would see changes in the pollen record, which we found within the sediments and the sedimentary rock. So we would see the appearance of certain crops, especially crops like cereal crops, like wheat, for instance. We would begin to see the percentage of pollen associated with wheat beginning to increase as they become cultivated and farmed on a more regular basis. We would also see a shift in the types of fossils you were getting. You would see a general move towards animals like goats and sheep and cows and pigs as they became domesticated, and as such they would begin to make up a larger portion of the fauna within certain areas, and you would obviously see that reflected in the fossils you were getting from certain locations. So there are lots of changes that human beings are making to the rock record, or making to the modern environment, which would be visible in the rock record. And so the idea of starting a new epoch and calling it the Anthropocene actually makes a lot of sense. Excuse me. But then in July 2018, something rather unexpected happened. The IUGS, which is the group of scientists who essentially oversee the geologic timescale, decided that no, we're not going to add a new epoch to the geologic timescale. Instead, what we're going to do is we're going to take the Holocene and we're going to split it up into 3 different stages. So the earliest stage, or the lowest stage should I say, would be called the Greenlandian, the middle stage would be called the Northgrippian, and then we have the final stage, which is the Megalaean. Now, each of these different stages do have distinct changes associated with them, which will be visible in the rock record. So the Greenlandian starts around 12,000 years ago, and the Greenlandian, or the change into the Greenlandian, is marked by the end of the last ice age. Now, the Northgrippian then begins to appear once we see very, very large-scale glacial melting. And this will have a significant effect because it's obviously going to release large quantities of fresh water which are going to go into the oceans. This is going to affect water circulation within the oceans, and as such it's going to have an effect on the types of marine sediments being deposited, and also to some degree the isotopic makeup of those marine sediments. And so we'll be able to see this transition from the Greenlandian into the Northgrippian in the sedimentary rock record. The final stage would be the Megalaean, and this is marked by a major change in climate. So we see a shift from the more slightly wetter, more temperate climate of the late Pleistocene to early Holocene, and we see a shift into a slightly more arid climate. So we would begin to see more temperate regions where you would have deciduous forests and grasslands being steadily replaced by more arid and semi-arid terrains. So the stages that have been proposed do make sense, and you would be able to see these changes in the rock record. However, when you actually look at these changes, none of them are actually associated with human beings, and the entire argument of the Anthropocene is to say that human beings have had such a major effect on the surface of the Earth that we should really start an entirely new epoch to take into account the significant changes which we have caused. So obviously this has led to a very, very large argument. At the moment the IUGS are winning because they're in charge of the geologic timescale, but the people who propose the idea of the Anthropocene epoch haven't given up hope yet, so that's one to keep an eye on for the future. So the transition from the Pleistocene to the Holocene is about 12,000 years ago, and it's defined by the start of warming conditions associated with the melting of glaciers at the end of the most recent ice age. So we see this change from the ice age, essentially the Pleistocene, to the post-ice age, the Holocene, by the fact that we see the deposition of till layers, the movement of temperate regions northwards, changes in vegetation, so we can also see that reflected in the pollen that we see outside equatorial regions, and we also see changes in oxygen isotope ratios for marine shelly organisms. So let's go through each of these 4 points individually. So why do we see a sudden increase in till deposition associated with the end of the last ice age? Well, the thing is glacial ice is absolutely stuffed with sediment, and that sediment ranges in size from tiny little clay-sized clasts all the way up to massive four-bedroom house-sized boulders. And so when the ice melts, well, that sediment has to be deposited, and that's exactly what we see as we transition from the Pleistocene to the Holocene. We see all this ice melting, and so all of this sediment contained in that ice has to be deposited, and it's deposited and it forms a rock which we call a glacial till. And so at the end of the Pleistocene we suddenly see the amount of glacial till increasing substantially, and this is showing us, right, the glaciers are now melting and they're obviously in retreat. Now, in terms of the movement of more temperate bands northwards, this is due to the fact the ice is melting. So as the ice melts, it will be retreating towards the north. Now, when the ice sheet was in place during the Pleistocene, it meant that large areas of the world, such as most of Canada, a large chunk of the United States, a very substantial part of Europe, and a very substantial part of Northern Asia, which under normal conditions would be quite temperate, so the kind of conditions we're used to now, well, those areas were covered in ice. And so this actually went and pushed the temperate band to the south. And so this meant that regions which we now consider dry, so for instance in the United States, areas like Southern California, New Mexico, Texas, during the last ice age would actually have been very temperate and very wet. And so what we see as the ice sheets are melting, we see the ice retreat north, and this allows the temperate band to move northwards. And so we see the temperate band leaving places like New Mexico, and we see this temperate band moving into more northerly states. At the same time, we begin to see areas like New Mexico becoming more arid, so we see them beginning to dry out. We also see changes in vegetation and the associated pollen outside equatorial regions. So once again, as these climatic bands start to shift, well, so we have the climatic band associated with the temperate zone, well, that begins to move north. And so as the ice is retreating, it was initially an area of tundra, which essentially is an area which is almost constantly frozen. And it's it's an environment essentially dominated by very, very low growing plant life. And so we see this tundra, which is associated with the ice sheets, being replaced by grasslands and deciduous forests. In places that were more temperate during the last ice age, like New Mexico, we begin to see changes. So we see the deciduous forest and the grassland disappearing as the area becomes hotter and drier, and we see it being replaced by plants which are more drought tolerant. And so once again, the reason we can see this movement of the temperate bands northwards is because we can see the changes in the vegetation and the sedimentary rocks as well. The final change we see is the change in oxygen isotope ratios, and there's a reason for this. So oxygen consists of 3 separate isotopes, oxygen 16, 17 and 18. Now we're interested in oxygen 16 and oxygen 18, so we're going to just ignore oxygen 17. Now oxygen 16 is by far and away the most common isotope of oxygen. Now what happens is during glaciations, lots and lots of water which has been derived from evaporated seawater essentially gets locked in the form of ice. And I'm going to explain why later on, but it just so happens that glacial ice is very, very rich in oxygen 16. And so this means over time what happens is you have water evaporating from the oceans, and the water molecules that have oxygen 16 in them are preferentially getting locked into glacial ice, so they can't return to the oceans. And so this means during the last ice age we start to see the amount of oxygen 18 beginning to increase relative to the amount of oxygen 16. So we have a change in oxygen isotope ratios. And so this increase in oxygen 18 shows us we have a period where we're forming lots and lots of glacial ice. On the other hand, when the ice starts melting, we begin to see an increase in the amount of oxygen 16 and a comparable decrease in the amount of oxygen 18 as it starts to get diluted as more of this water is essentially put back into the oceans as the glaciers are melting. Now, we can analyze these changes in the oxygen isotope ratio by looking at shells. So shells are on the whole made of calcium carbonate. So calcium carbonate, of course, consists of 1 carbon and 3 oxygens. Now, in order for the calcium carbonate to be stable, it has to be in equilibrium with the surrounding environment. And one of the types of equilibrium that it will be in is an isotopic equilibrium. So this means the oxygen isotope makeup of the carbonate is going to have to match the oxygen isotope makeup of the seawater. And so this means that what we can do is we can come along and we can analyze the shells and we can measure the oxygen isotope ratios of the calcium carbonate, and that will essentially tell us what the oxygen isotope ratio of the seawater was. And so by doing this we can essentially, number one, we can date layers of sediment by looking at the different microorganisms that have these calcium carbonate shells, and then we can analyze those shells and we can say, right, well, we can quite clearly see a spike in the amount of oxygen 18 here. This is telling us we have the onset of glaciation, and here we can see a steady decrease in the amount of oxygen 18 and an increase in the amount of oxygen 16. So this is showing us the glacial ice is melting. And so when it comes to the end of the last ice age, obviously we see the amount of oxygen 16 going up as the glacial ice is melting, releasing that oxygen 16 water back into the ocean basins. So the Pleistocene is often referred to as the Ice Age. So during this epoch we have extensive ice sheet coverage in the northern hemisphere especially. So these ice sheets are covering a substantial portion of northern North America, Northern Europe and northeastern Asia, typically above a latitude of about 45 degrees north of the equator. Now, during the same time period, there were extensive ice sheets covering Antarctica, just like the present day. However, we're uncertain whether these ice sheets extended beyond the coastline of Antarctica, so whether these ice sheets extended out into the Southern Ocean. So one of the issues is that ice is perfectly happy when it's on continental crust, because continental crust is nice and solid. However, once ice sheets start to move out over open water, typically they begin to become unstable because the weight of the ice allows the ice sheet to just sag into the sea. Now, I know ice will naturally float when it's on top of water, but we're talking about, in some cases, up to 3 kilometers worth of ice. This is a very thick layer. And so a layer this thick will not be able to support its own weight on something so weak as seawater. And so what will happen is we often get ice sheets breaking up when they make it to the oceans, and obviously the breakup of these ice sheets leads to the formation of icebergs. So whether we will have been able to have formed a thick, extensive ice sheet that actually managed to push out into the Southern Oceans is somewhat debatable. It's more likely that what you had during this time period is you had Antarctica being completely covered in ice, and you had the ice sheets extending a very short distance into the Southern Oceans, and then outside of that zone you then probably had a big band of what we refer to as pack ice. And pack ice is where the sea is covered in essentially greater than 70% ice. And so what you have are lots and lots of pieces of ice with small, thin channels of water in between them. You might have seen pictures of it, for instance, on nature documentaries. And so there's a good chance that the ice sheets of the southern hemisphere during the last ice age may not have been continuous. It was probable that Antarctica had quite good ice coverage, but most of the Southern Ocean around Antarctica was probably covered in pack ice rather than one solid, consistent ice sheet. Now, the Pleistocene is marked by extensive till deposits because obviously we have lots and lots of glaciers. So lots and lots of glaciers means lots and lots of glacial ice, and this means high levels of till formation and therefore till deposition. We also have the glacial ice polishing and striating bedrocks, because one of the things we have to remember is that a glacier is like a bulldozer. As it moves over the terrain, it will strip away vegetation, it will strip away soil, and so this means the glacier is resting directly on the bedrock. And in the bottom of your glacier you have lots and lots of fine pieces of rock, and so as that glacial ice moves over the bedrock, those little fine pieces of rock will literally polish the bedrock, a bit like using a piece of sandpaper to sand down a piece of wood to create a nice smooth finish. And so this process of polishing the rocks is, essentially produces what are referred to as glacially polished rocks, and it's an indicator of a glacier having moved through the area. Now, within the bottom of the glacial ice, you also have some larger clasts, so we're talking things like cobbles and boulders. Now, these larger clasts, as they get dragged across the bedrock, they will actually scratch grooves into the bedrock, and these are referred to as striations. So another thing we see as we move into the Pleistocene is we see the amount of polished and striated bedrock substantially increasing, and this is showing us the glaciers are expanding out, especially in the northern hemisphere. Now, we also see an increase in U-shaped valleys during the Pleistocene. So U-shaped valleys are associated with valley glaciers. So these are the types of glaciers we get in mountain ranges. And they produce a very, very distinctive valley shape that has very, very steep near vertical sides and a flat bottom. So it essentially in profile, it looks kind of like an uppercase letter U. And so once again, the increase in these U-shaped valleys is showing us that we have an increase in mountainous glaciation. So essentially that's also going to suggest that global temperatures are dropping, and this is an indicator that we have a large-scale glacial event taking place. So once again, in the Pleistocene, we look for extensive till deposits, polished and striated bedrock, and U-shaped valleys, and each of these is associated with the expansion of the glaciers. Now, glaciers and ice sheets are moving bodies of ice, and they move by two methods. There's plastic flow and basal slip. So plastic flow is simply the ice deforming in response to pressure. So think of a piece of Play-Doh or silly putty. You hold it in your hand, you squish it. Essentially, you are changing the shape of that Play-Doh or silly putty by applying pressure to it. Exactly the same thing happens with the ice. As weight gets put on the ice in the form of new snow or ice, the ice down at the bottom, essentially, begins to deform in response to the new added weight. And so this deformation will result in the ice flowing like water. The other method through which the ice moves is through glacial slip, and this is simply the process of your piece of solid ice sliding over the bedrock. Now, glaciers come in three types. The first type are valley glaciers, and these are the ones that we're actually most familiar with because the vast majority of modern glaciers are valley glaciers. So we get valley glaciers in mountainous terrain, and they are long, narrow bodies of ice which are confined to mountain valleys. And the ice will essentially form at a topographic high point and it will flow downhill under gravity. So you'll get this long linear body of ice, sometimes referred to as a river of ice. And in terms of valley glaciers, they move by both plastic and glacial slip. The reason for that is on the whole, valley glaciers are the smallest type of glacier, and as such, because they're not really huge bodies of ice, the weight of them allows a certain amount of movement due to glacial slip because they're not that heavy, and obviously the deformation of the ice through plastic flow is going to be the result of new ice being added to the end of the glacier, essentially pushing older ice downhill. Now, in terms of larger glaciers, we have two types. In fact, you know what, before I start on that, here we actually have an image of a valley glacier. You can see here's the high terrain on one side, here's the high terrain on the other side. So we're obviously in a mountain valley, and you can see essentially the glacier itself is forming a linear ribbon of ice, essentially a river of ice. And so the ice itself is going to start up here at the high terrain, and it's going to move downhill under gravity until it comes to the end of the glacier where it melts. Now, the thing about valley glaciers is obviously because they've got high ground either side of them, they can't actually escape the river valley. They're trapped there. Now, the other two types of glaciers, continental glaciers and ice caps, they are unconstrained. They go where they want to. Now, continental glaciers cover an area of at least 50,000 square kilometers. So, continental glaciers are unconfined by topography and they flow out from a central point or points. So obviously a continental glacier is going to form somewhere, and as that continental glacier grows, it's going to move away and grow larger from that central location. Now, in the case of continental glaciers, most of the ice movement is accommodated through plastic flow. And this is because ice sheets associated with continental glaciers are very, very thick, so they're very, very heavy. So the weight of them is often so great that the ice cannot slide over the bedrock. So that means the only way the ice can move is therefore in response to pressure, and so it's plastic flow that drives the movement of the ice. Now, in terms of continental glaciers, we have two modern examples. We have Antarctica and we have Greenland. In both cases, you can see we have an ice sheet covering nearly both of these. Well, in the case of Antarctica, continent; in the case of Greenland, a subcontinent. And we can see that these ice sheets are unconstrained. They're just going wherever they want to. Now, between valley glaciers and continental glaciers, we have an intermediate glacier size, which are referred to as ice caps. So an ice cap is exactly the same as a continental glacier, but it simply has a surface expression of less than 50,000 square kilometers. So it's very common for people to refer to large bodies of ice like Antarctica or Greenland as ice caps, but in reality they're not. They should in fact be classified as continental glaciers. So during the Pleistocene there were several episodes of glaciation. So it wasn't like there was just one event where the glaciers started growing and then eventually the glaciers retreated. It wasn't like that. What you had is you had a stepped growth. So essentially the glacier would grow for a bit, it would retreat a little bit, it would start growing again, it would retreat a little bit, it would start growing again, it would retreat a little bit. And so every time the glacier is growing, we essentially typically call these periods of glacial expansion. Now, in between these periods of glacial expansion, we're going to have short periods where the climate warmed up and we have some glacial retreat, and these are referred to as interglacial intervals. Now, at the maximum extent of the ice sheets associated with the last ice age, the ice sheets would have covered about no more than 30% of the Earth's continental surface, with the vast majority of that having been in the northern hemisphere. Because once again, in the northern hemisphere, we have North America, Europe and Asia. We have big pieces of continental crust on which you can form nice, large, stable ice sheets. In the case of the southern hemisphere, we obviously have Antarctica, but as soon as you move off the coast of Antarctica, you are straight into a large body of water. And as discussed, ice finds it more difficult to support itself when on bodies of water. And so this would have helped to limit the size of the southern ice sheets to some degree. Now, in terms of temperatures during the last ice age, temperatures would have been about 4 to 7 Celsius lower than present. And one of the drivers behind this will simply be the change in the Earth's bond albedo during the last ice age. So what we're doing during this time period is we are replacing dark coloured continental crust and dark coloured ocean water with light coloured ice. And so the fact this ice is so light in colour, well, that means it's going to reflect more sunlight back into space. And so this means the amount of solar radiation being retained by the Earth substantially decreases as the amount of ice cover gets larger. So as the ice sheets got bigger, essentially more solar radiation gets reflected back into space. The Earth therefore got cooler. So, as we've discussed, the lower temperatures caused the more temperate regions to move south, and so regions which you consider temperate now, like the southern Canada and the northern states of the US, most of Europe and quite a lot of northern Asia, well, those more temperate bands began to shift to the south, and so this means that areas which we now consider dry, like the Sahara or New Mexico in the United States, for instance, actually had greater degrees of precipitation because during the last ice age they were temperate zones. And so we see things like the Sahara being covered in wide-scale forests. Now, it's uncertain whether we've actually moved out of the most recent ice age, or whether we're actually in one of these interglacial intervals. And once again, this is something that's being argued over by geologists. Now, to be clear, chances are we probably have left the most recent ice age, but there is still a chance we could be in an interglacial and things could start to cool down again, obviously assuming we get a handle on global warming. So now let's move on to Quaternary Technism and Volcanism. So you're not going to be too surprised when I tell you that Quaternary plate tectonics and volcanism were operating in pretty much exactly the same way as they do now. And this is because, of course, the present day is part of the Quaternary, and not much has changed over the past 2.6 million years. So in terms of the Alpine Himalayan and Circum-Pacific orogenies, which are the bigger orogenies which are going on now, things were operating in exactly the same way as they do in the present day. In terms of plate tectonics in general, rates of convergence at convergent plate boundaries and rates of seafloor spreading at divergent plate boundaries were pretty much the same as they are now, so no substantial differences there. In terms of North America, well, we see stresses caused by the movement of the San Andreas Fault along the western side of North America, leading to the formation of faults and folding in the west and southwestern United States. In terms of volcanism, we see volcanism along the west coast becoming limited to the Cascade Range. So that's essentially a portion of the west coast of the North America, which extends from Northern California through Oregon, through Washington State, and into British Columbia in Canada. Now, this region is, of course, the location of a subduction zone, where we have the Juan de Fuca plate subducting underneath the North American plate. And so, of course, the subduction of the Juan de Fuca plate is going to lead to magma generation, and so that helps to explain why we have volcanoes forming in that area. In terms of other areas of North America which were once volcanically active, we see those areas becoming quieter because of course we have a shift from convergent plate tectonics to transform plate tectonics. So we have the San Andreas Fault to the south of the Cascade Range, and we have the Queen Charlotte Fault or the Fairweather Fault to the north of the Cascade Range, and both of those are transform faults, and so of course they do not generate any kind of magma. Now, volcanism in the Cascade Range became more pronounced in the Quaternary, and it led to the formation of several large composite volcanoes and lava domes. So a classic example of these volcanoes would be Mount Rainier or Mount St. Helens, for instance. Now, in terms of North America as a whole, we see sporadic volcanism continuing, but this sporadic volcanism represents the latter stages of the volcanic activity which began in the Paleogene and the Neogene. So these are dying systems. Most of this volcanic activity is seen in areas like Arizona, Idaho, and California. Now, we do see some volcanic activity associated with a hotspot, which is trapped underneath North America. So this hotspot has led to the formation of a band of volcanic deposits, which stretches from modern-day southern Oregon through Idaho and into Wyoming, and more accurately, the Yellowstone National Park area. So in the Yellowstone area, we see substantial eruptions taking place around 2 million years ago, 1.3 million years ago, and 0.6 million years ago. And these led to the formation of a large caldera that measured about 76 by 45 kilometers. Now, this caldera has been filled by more recent volcanic deposits, mostly tuff, and these volcanic deposits were put down at between about 150 and 75,000 years ago. Now, the interesting thing about the modern Yellowstone area is that we can see that the crust is actually rising slightly in the Yellowstone region. And this would suggest that the magma chamber which underlies the Yellowstone caldera is beginning to refill, and eventually, if the magma chamber refills sufficiently, it could lead to a very large volcanic eruption. So now let's move on to Pleistocene Stratigraphy. So we're going to start by thinking about the continents. Now, we know that during the last ice age, the northern hemisphere continents, so that's North America, Europe and Asia, were partially covered by very substantial ice sheets, and obviously these ice sheets are going to lead to the generation of large amounts of glacial deposits. So through the analysis of these glacial deposits, which are mostly made of glacial till, the analysis of moraines, which essentially are piles of glacial till that build up along the edges of the glaciers, erratic boulders, which essentially are, as the name suggests, boulders which were contained within the glacial ice, but they get dropped as the glacial ice melts and retreats, and the polished and striated bedrock, which is created by the movement of the glacier. We have managed to determine that the glacial maximum during the Pleistocene covered an area of approximately 45,000 square kilometers. Now, this is about 3 times more of the Earth's surface than is presently covered in ice. So at the moment, we have about 10% of the Earth's surface covered in ice. That works out to be around 15,000 square kilometers. And in terms of the ice depth during the last ice age, it probably reached somewhere around a maximum depth of about 3 kilometers. So these would have been very substantial ice sheets in some locations. Now, in North America, we've managed to map the glacial deposits, and this has revealed several stages of glacial expansion and retreat. So you need to remember that when a glacier grows, it doesn't just, grow and then retreat. It's a staggered process. So the glacier will grow for a while, it'll retreat for a little bit, it'll grow for a while, retreat, grow, retreat, grow, retreat. And so, if there's essentially at the end of that a net growth, the glacier will move forward. If there's a net retreat, then the glacier will move backwards. Now, these periods of glacial expansion are separated by periods where the conditions get slightly warmer, and these are referred to as, of course, interglacial intervals. Now, as the mapping of glacial deposits has become more refined, we've actually managed to work out that there are 14 stages of glacial expansion during the last ice age. Initially we thought there were 4, but over time we've managed to refine the model and pick out more individual events. Now these 14 stages are split into pre-Illinoisian A through K, the Illinoisian, the Sangamonian, and the Wisconsinian. And if you look here, you can see here's a geologic timescale, and you can see these periods of glacial expansion marked out here in the right hand column. Now, analysis from other areas reveals similar stages, but the number and terminology varies. So if we were to go to, let's say, northern Sweden, we would also see glacial expansion at around the same time. We would see the glaciers would expand and then retreat, expand and then retreat, expand and then retreat. However, the number of expansions and retreats and the timing of those expansions and retreats would vary slightly between our two different locations. Now, this is due to the very chaotic nature of glacial deposits. So you can't guarantee that one glacier, let's say in North America, is going to behave in the same way as another glacier, let's say situated in Scandinavia. So that's our first problem. The other problem is that as a glacier moves forward, it will very often roll over the top of glacial deposits from earlier glaciers. And as we've discussed, glaciers are essentially bulldozers, so it's not uncommon for a glacier to destroy pre-existing glacial deposits, meaning obviously once they're destroyed they're not part of the rock record, so we essentially don't know they ever existed. So obviously this is a problem. Now, it must be remembered that a glaciation is not a single event. As discussed, instead it contains several phases of expansion and retreat, which are obviously going to further complicate things. Now, the deposits are difficult to correlate on a local scale, so trying to correlate on a global scale is nearly impossible. So one of the problems we have with glacial till is it's a very difficult rock to date. We don't have much by the way of life associated with glacial deposits, and so that means fossils are extraordinarily rare. And so this obviously makes it very difficult to date these glacial deposits. So if you're trying to date a glacial deposit in North America and you're trying to, see whether it's the same age as a glacial deposit from, let's say, Siberia, well, it's going to be nigh on impossible to do. And this is one of the problems, when we say that during the last ice age we had this massive glacial expansion, well, that's a little bit difficult to prove universally because we don't have exact correlations between different locations because we can't date the glacial sediments. So so we talk about these ice sheets all moving forward as if they were one large mass, whereas in reality some areas might have moved forward faster than others, some areas might have retreated faster than others, and that's difficult to prove definitively because the dating evidence is so difficult. So over the last 50 years or so, scientific groups have managed to get hold of sedimentary cores from the deep marine environment. And the bit of the sedimentary sequence that we're most interested in is, of course, the sediments that were being deposited in these deep marine environments during the Pleistocene. Now, what we can do is we can go through this sedimentary sequence layer by layer, and we can sieve the sediments, and we can actually extract the calcium carbonate shells of the little microorganisms that were living in the seawater. And so what we can do is we can analyze those shells for the oxygen 16 and oxygen 18 concentrations, and we can use that to produce an oxygen isotope ratio. So if you remember, the oxygen isotope ratios of seawater will change as the amount of glacial ice increases and decreases. So as the amount of glacial ice increases, so we have a glacial expansion, oxygen 16 rich water gets preferentially locked up in the glacial ice, and so when we look at seawater, we see during those time periods of glacial expansion, we see the amount of oxygen 16 in the seawater dropping, and comparatively speaking, the amount of oxygen 18 in seawater increasing. When the reverse happens and we have a glacial retreat, well, this glacial ice melts. That obviously allows large quantities of oxygen-16 rich water to re-enter the ocean basins, and so we see a change in the seawater composition. We see the amount of oxygen-16 going up in the oceans, and comparatively speaking, we see the amount of oxygen-18 going down. And so what we can do is we can use these oxygen isotope ratios as a crude gauge for ocean temperature. So we can say, right, was the seawater getting hotter or was the seawater getting colder? Obviously, when it gets colder, that equates to a glacial expansion. When it gets warmer, that essentially equates to an interglacial, so when it gets warmer. Now, by looking at this data, we've managed to identify 20 warm-cold cycles which occurred during the Pleistocene. Now, this is obviously 6 more than the 14 that we've managed to identify from terrestrial sediments, but this is perfectly reasonable because, as we've discussed, glaciers are like bulldozers. So as there's a glacial expansion going on, it would not be surprising for an expanding glacier to erode away previously deposited glacial sediments, and so that would mean obviously we're losing this information. It's being removed as the glacier expands, and so it's not surprising that 6 of these warm cold cycles are missing from the North American record. So now let's think about Pleistocene stratigraphy with regard to the deep marine environment. Now, initial attempts up until the 1960s to constrain the number of Pleistocene glaciations were limited to terrestrial deposits because those were the ones we can actually get at. Now, as the technology required for deep sea drilling improved, it was discovered that deep sea sediments, so these are abyssal plain oozes and clays, offered a useful window into the global climate in the Quaternary. So these deep sea cores are being produced by oil companies. So oil companies are obviously interested in the rocks which contain oil. But in order to get to those rocks in the seafloor, they obviously have to drill through the sedimentary cover that's sitting on top of the rocks. And so what happens is, as part of the drilling program, these oil companies will often produce quite large amounts of sedimentary marine cores which they don't have any use for. And so they will give those cores to scientific institutions for study. And so these cores have allowed us to essentially look at changes in the environment during the Quaternary in extremely high detail, primarily using oxygen isotope data. Now, the thing we need to remember about these deep marine sediments, or pelagic clays as they're sometimes referred to, is that they're being deposited onto the abyssal plain, and so they don't get eroded because there's no erosion on the abyssal plain. And so this means what we have is a continuous sequence of sediments being deposited, and we can feel safe that no sediment has been lost. And so this means we have a continuous sequence all the way through the Quaternary, which is absolutely great. Now, within the clays, the thing we're most focused on is finding the shells of Foraminifera. These are little single-celled zooplankton that live in seawater. Most of them have, they all have calcium carbonate-based shells. And obviously, when the organism dies, the organic portion decomposes, but the shell, the calcium carbonate shell, will survive, and it will sink down to the seafloor, and it will become incorporated into the abyssal plain sediments. And then obviously we can come along later, we can extract the shells from the layers of sediment, and we can then analyze them for their oxygen isotope information. But that's not the only thing we look at. So Foraminifera are useful, in terms of helping us to gauge seawater conditions, because the vast majority of Foraminifera have relatively limited conditions for growth. So most species of Foraminifera have essentially a set temperature range in which they're comfortable. So the first thing we can do is we can simply look at the species of Foraminifera to help us gauge, was the seawater warm or was the seawater cold? So by looking at the Foraminifera contained within these marine sediments, we can use them to essentially work out the type of Foraminifera. Was it a hot water Foraminifera or a cold water Foraminifera? We can also look at the coil direction of the Foraminifera. So a lot of Foraminifera have shells which are spirals, and sometimes the spiral will be clockwise and sometimes the spiral will be anti-clockwise. But for some species, the direction in which the shell coils will actually change depending on the temperature. And the final thing we can use these foraminifera shells for are obviously the oxygen isotope information. So let's start by thinking about temperature. So many foraminifera are sensitive to temperature, and they will migrate to different latitudes as the surface water temperature changes. So as we discussed during the last ice age, what we saw the ice sheets moving south, and this pushed the temperate band towards the equator. And so we can see that as there's a glacial expansion, we begin to see more temperate foraminifera moving into areas which were tropical. So this is telling us the temperate band is being pushed south, and that's obviously a result of the ice sheets expanding. So a classic example is during a period with a cooler global climate, one particular foraminifera called Globratalia will be restricted to near equatorial regions, so it's quite a warm water species. Now what we can see is as the global temperatures begin to increase, we will begin to see it moving to higher latitudes, so we will see it begin to appear within the sedimentary record as the seawater begins to get warmer. And so just by finding this one foraminifera, we can say, right, seawater temperatures are clearly increasing. So now let's think about coil direction. So as discussed, a lot of foraminifera have shells which are spirals, and the spirals can obviously go in a clockwise or anti-clockwise direction. Now, as I already mentioned, certain species of foraminifera which have these coiled shells are temperature sensitive, and a change in temperature can actually cause the shell to coil in the opposite direction. So once again, the classic example of this is Globratalia, and this will coil to the right in warm water, so temperatures in excess of 10 Celsius, or it will coil to the left in colder water, so that's temperatures lower than 8 to 10 Celsius. And so this gives us once again a very crude gauge of whether the seawater was getting warmer or whether the seawater was getting colder. The final type of analysis that we can do on the sedimentary cores is oxygen isotope analysis. Now, we know that oxygen isotopes come in three varieties: oxygen 16, 17 and 18. And we're most interested in oxygen 16 and 18, and that's for two reasons. The first reason is that oxygen 16 and oxygen 18 are just the two most abundant oxygen isotopes, and so that's going to make them easier to measure because they'll be present in the highest concentrations. The other reason that we're interested in them is because there is a significant difference in weight between oxygen 16 and oxygen 18. So oxygen 18 contains 2 more neutrons than oxygen 16, and this is going to become important. Now, what we know is that water molecules that contain oxygen 18 are going to be heavier than water molecules that contain oxygen 16 by the aforementioned 2 neutrons. So what we know is that water molecules that contain oxygen 18 are more difficult to evaporate, so they're more difficult to take from a liquid to a gaseous state, than water molecules that contain oxygen 16. So this means that if you were to have a jug of water, and in that jug of water you had water molecules that contained oxygen 18 and water molecules that contained oxygen 16, well, as you heated up that jug of water, the oxygen 16 bearing water molecules would preferentially evaporate when compared to the oxygen 18 bearing water molecules. And so this means the water vapor that's produced will naturally be more oxygen 16 rich. Now, the other thing that we know is that if you were to take water vapor in the air and you begin to condense it, it is energetically more favorable to use oxygen 18 bearing water to produce raindrops versus oxygen 16 bearing water. And so this is going to have an effect on the oxygen 18 level in the atmosphere, because of course the longer the water vapor is in the atmosphere, the more time there is for rain to form, and so that gives more opportunity for oxygen 18 rich water to be stripped out of the rain cloud. So because we have these differences between oxygen 18 and oxygen 16 bearing water, it means that water vapour that enters the atmosphere will be enriched in oxygen 16 bearing water versus oxygen 18 bearing water, and that any precipitation that forms from that water vapour in the air will naturally be more oxygen 18 rich versus oxygen 16. Now, this means that as global temperatures decrease, it's going to cause lower temperatures to migrate towards the equator. We've discussed this. So as the ice sheets expanded, it pushed the temperate zone further south, and obviously the temperate zone moving further south is going to compress the equatorial region. So the equatorial bands, the tropics, are going to get narrower. Now, this means that water vapour rich air, which is essentially forming in these tropical regions, is going to be produced through evaporation. This water rich air is going to start moving towards the poles. Now, because these lower temperature bands have migrated south, it means that the air will cool down sooner, and therefore precipitation will begin to form at lower latitudes, so closer to the equator. And so this means that almost as soon as your water-rich air leaves the tropics and starts to move either north or south, the temperature is going to start dropping, it's going to start forming precipitation, and so we instantly start to strip oxygen 18 bearing water out of the air in the form of rain. Now, this stripping of oxygen 18 from the atmosphere is obviously going to affect the oxygen isotope composition of the moisture cloud as it moves further north or further south. So over time, as your water-rich cloud moves towards the poles, it's going to steadily become more and more oxygen 16 rich. And that's because as it moves into these higher latitudes, it's had more and more time to lose oxygen 18 bearing water in the form of rain. And so this means that the precipitation that falls in these high latitude areas, which were covered by ice sheets, the precipitation is going to be very oxygen 16 rich, and so this means the ice that forms from that precipitation is also going to be oxygen 16 rich. And so what this means is that glaciers will essentially lock up oxygen 16 bearing water. And so this means that, comparatively speaking, the amount of oxygen 18 in the oceans is going to go up slightly. Now, as we've already touched on, we know that carbonate must be in isotopic equilibrium with the seawater around it. So we know, of course, that calcium carbonate contains 3 oxygen molecules, and so we know that the oxygen molecule isotope ratio has to be the same as the seawater. And so we can use the oxygen isotopes of the shells to essentially give us an idea of what the oxygen isotope ratio of the seawater was when that carbonate was being precipitated. So by finding shells within these marine sediments, we can analyze them, and where we have shells that show us a high oxygen 18 oxygen 16 ratio, we can see we were in a period of large scale glaciation because we have oxygen 16 being locked up in glacial ice. Where we have shells that give us a lower oxygen 18 oxygen 16 ratio, this will represent an interglacial period. So we have oxygen 16 bearing water re-entering the ocean basins as the glacial ice melts. Now, the one thing we need to remember is that all of these observations that we can make from these marine cores do not produce solid numbers. They simply allow us to work out relative temperature. Was the sea getting colder, or was the sea getting warmer? So the final thing we need to remember is that we can't actually correlate between the cooling warming events that we see in these deep marine sediments and the cooling warming events that we see represented in the terrestrial sediments that were being deposited during the Pleistocene. Now, the reason for this is that there's a lag between the temperature changes that we see on land and the corresponding temperature change that we see in the oceans. So if we think of a glacier, so the glacier is going to start expanding, that's obviously going to drive down temperatures on the continents. Now, it's actually going to take a little bit of time for this temperature change to be registered by the oceans. And so this means there's going to be a little bit of a lag. So when in the continental sediments we can see the glaciers expanding, for instance, it takes a little bit longer for this expansion to be registered in the marine sediments. And so this means we can't correlate directly between these events because there is an ever so slight difference in age. And we always need to bear that in mind. So when we're talking about these 20 cooling warming events that we can see in the marine cores, and we compare them to the 14 heating cooling events that we can see in the terrestrial sediments, well, it can be at times a little bit difficult to work out which of these events correlate with each other. And so, we always have to bear in mind that the record we have is to some degree going to be incomplete. Okay, so this is it for part 1. So please get up, have a walk around, go and get a glass of water, take 5 or 10 minutes to relax, and then please come back for part 2.